Andreas has done a lot of things. He was got his PhD at the University of Wisconsin, and he's been largely at the University of Toronto as a professor there since then. However, as you can see, if you have really excellent eyes, he's taught at a large number of prestigious places, including Northwestern University, just adjacent to where we are now, the Hellenic Open University in Greece, and EPFL, École Polytechnique Fédérale de Lausanne in Switzerland, and he's the director of the NSERC COHESA Research Network at the University of Toronto, and because of all the amazing research he's done, he's a fellow of both ACM and IEEE, and so he's going to give a talk today, as you probably know, on boosting machine learning innovation, the computing systems that learn and adapt, and I really look forward to his talk, and welcome, Andreas.
Thank you. Thank you. Cross my fingers.
By the way, sorry, just before you start, we allotted about 45 minutes per speaker and then 10 minutes for discussion, but certainly if you prefer to get all questions, wait till the end, we can do that, but otherwise, please speak up in the middle, so whatever is your preference.
First of all, thank you for the very nice introduction. Thank you and to all the organizers for the invitation. It's very nice to be back at Micro after I don't know how many years now, 2.5. Thank you all for waking up this early. I don't know if some of you may be jet lagged or not, but I appreciate you being here. I'm not a morning person, so it's a great sacrifice which I don't take for granted from all of you. I appreciate that. Since we do have all day, the next person is not here, I'll be happy to stay. Of course, as if this was a class, you should feel free to leave any time. I'm not going to be offended, right? People have their lives and they have their own program. So feel free to stop any time and ask. My intention was to do a high-level introduction to some of the most recent work we've done at our group. It hasn't yet, most of this stuff has not yet been published. We've been trying, but that's a different discussion we can have over coffee if you want afterwards. This is not my own work necessarily. This is work that has been done at my group. Tons of great people have worked on that, so I'm not going to go through all of them. And early on, we also collaborated with some people at U of T and at UBC, British Columbia, and as well. So, but the work I'm going to be presenting today is work from the group itself. Now, as people get older, we reminisce a little bit. So usually when I give this talk, I like to give a bit background about myself. I'm going to go through this very quickly. So sorry if I'm doing the old guy and I'm getting all these things. Sorry. So I started playing with computers mid to early 80s. I was lucky enough, one of my close friends, who's still a friend, he bought this machine back in Europe. This machine, it was nice because he forced you to program, right? Whenever you got it, you would get a prompt, and it would say, write something. Even if you want to play a game, you have to take a cassette player, wait 15 minutes, still you have to write some command. It had a very nice programming language, and I hope you get it, but sometimes I'm going to be sarcastic in what I say. I'm sarcastic in that. It was called BASIC. No subroutines, no nothing. And you were writing like a huge code down to do your program. It was, somehow this felt interesting to me, and somehow, like other things in school, they seemed easy to me, right? Again, this doesn't mean they were easy. This is what I felt, right? That's how it felt to me. And I felt this is good. I mean, anybody can write programs, right? Who cares about that stuff? I mean, this is for the plebs. It's not an interesting thing. What's interesting is building this thing. So even as a teenager, I wanted to build chips, right? We got to build one chip this last summer for a very different reason, but this is what I felt is important. But then, as I grew a little bit older and wiser, you can say that, I realized that when you build this chip, what you're building is you build this, right? A hammer or whatever you want to call it, screwdriver. By themselves, they're not very useful. Right? If you take a computer, you put it on your desk, it doesn't do anything. What you have to do is you have to put an interesting algorithm, that program inside it, and it's all the expertise that goes into that algorithm that makes this thing useful. Yes, without this, you cannot take it's not like a hammer, right? You cannot take a stone and replace a computer. You still need it. But on its own, it's nothing, right? I do take solace, though I decided I'm going to work in Harvard, at least pretend that I do. At the end is that the tools we're building are not like hammers. They're really very universal tools. People have been using them for anything and everything, and the things they use them for has been increasing. Right? So we're kind of relevant. However, on the other hand, let's not forget this is the micro community, this is the architecture community. We're not necessarily the people that build these machines, others are building. And it's not necessarily just because we say something or we publish something that we have an impact in the real world. So let's keep that aside. With that said, my research for the past, I would say 8 years now, has been on enabling, that's what I say, my marketing, further innovation in machine learning. Right? I was lucky enough back in 2009 to offer a course in Toronto, which was the first course in teaching CUDA. There was a very nice book, one named Hu, and his co-author on how to program machines in CUDA, GPUs, and this was the first offering. My chair asked me, would you like to do that? And I had an interest in understanding what the GPUs were. A person named Alex Krivevsky took the course. If you don't know who Alex Krivevsky is, you know AlexNet, so that's the connection over there. And he did a convolutional layer as his class project. He came to my office, he showed me this cipher images, tiny ones, like, I don't remember, 12, 32, 32, and I was saying, who's going to be interested in this stuff? I mean, why do you care about that? So it's not as if I saw the light or anything, but it was the time where I was trying to look for something else. I did talk to his advisor, but they had better things to do, obviously, right? Obviously. Later on, though, I managed to connect with some people in Toronto, so I was doing machine learning, so I got interested in this fairly early on. So I got lucky, like many other things in my life. Many things I got lucky, many things I didn't. That's how we started that. However, let's not forget, I am a computer architect at heart, or at least I pretend to be. So, what is our philosophy here? What we realized, anyway, our strategy, if you want to call it our strategy, was the following. We were thinking, everybody's going to pick up on this. This is so important, right? You have a machine that seems to be listening to you, seems to be seeing things, right? Seems to be able to speak to you, right? So it looks like a human person, not necessarily, right? But I'm just saying it goes over that, and this is taking the store of every other field in computer science. So people have been working on computer vision for ages. Somebody that plops at machine learning network, they wipe everything clean, right? Because they're doing it much better. So we're thinking everybody's going to pick up on this. The big guys, Googles, the Nvidias, the whatever, they're going to spend tons and tons of money. These are very clever people, right? A lot clever than us. A lot of experience, but they have to deliver products. They're going to do the most important things first. So we wanted to come in and help them and say, 5 years on the line, once you do all the stuff that's very hard to do, but it's obvious that you need to do, what's going to be next? So our first rule of thumb was the following. Machine learning, yes, the algorithms have been around for a while, but they're evolving, right? So if you were, the word transformer, I don't know if it existed in 2013 or 2014 or 2015, right? Attention is all you need came much later on. These things evolve. And writing software, as much as I would like to say it's easy, it's not. It's a very complicated thing. And the last thing you want is you want to take your program and say, oh, you're going to change your algorithm for me, so it runs nice on my machine. So we wanted to stay as much as possible hidden beneath whatever compiler you have, runtime and hardware. And because my expertise, if I have any, is in hardware, we focused on this. So try to do as little, require as little, possibly nothing from the programmer, and give them a machine that's going to be more capable in running these neural networks. Right? That's the idea here. And if possible, give them an incentive. That is, if they try to do optimizations of the network, reward them for them. If they will try to prune, if they try to quantize, build hardware that will follow them along that path and reward them for taking that effort. The other thing is the classical thing of effort versus reward. I mean, this is a lesson learned in life. I think most of us have understood this by now. You spend a little bit of effort, you get a lot of reward. And then, if you want to get there, you require a lot of effort. Human nature being what it is, when you try to optimize something, and this is how I was or how I am, you try to get there. You try to get everything, right? Every single case has to be the best possible. The end result in my experience is you end up here, if not down there. Right? You put all the effort, you covered all the bases, whatever, and guess what? Well, that's not most of the time. So we try to stay on this curve as much as possible and put some effort and get the most reward out of this. Now, this is the other marketing slide. It's a wall of text, a lot of stuff. This is, since you're going to get the slides, I guess it's nice for you to know that. What I'm going to talk about today, this is the real talk now. Right? I'm going to talk about three things. These are the most recent pieces of work from our group. This has been developed over 4 years. It's still unpublished. Moki was published in this year. Right? This is lossless compression techniques for physical inference. I'll tell you what it is. I'm going to spend most of my time here. Multi-user quantization for transformers comes with hardware as well. And strong here is a floating point is our approach to accelerating training. And I'll explain what's going on. So, welcome to the talk now. Let's talk business. Let's talk the actual stuff. Here's the high-level, mile-high view of a layer. I gave this talk in Montreal. That's why I had put in there. I should have sent this talk, but I didn't think of it. Sorry. Right? So you take something, it goes through a bunch of processing layers, and at the end you get an answer. This is an image classification network. We all know there are many different types of networks. At the end, though, when my mom picks up the phone and says, Andreas, what do you do for a living? Well, I try to do this fast, as much as possible. It's really, really, really completely anticlimactic, right? Because you just do a lot of multiplying calculations as much as possible, as fast as possible with as little energy as possible. Now, so at the end, accelerating training, accelerating inference or training ends up, from the hardware perspective, building machines that can pull in massive amounts of data, do massive amounts of multiply accumulates, and pulling out the results. And keep doing that repeatedly, right? So we have these two things to optimize. Very easy to say, right? Sure, two things. And we all know that's what architecture is at the end, because that's what a computer does, moves data around and does computations. It's just that this has very, very specific properties we can take advantage of. And then, because my first foray into computer architecture was general purpose processors, and this is in the 90s, right? The goal there was to build machines that actually do this. They don't do what you tell them to do. They try to do it better than you say them. Like, that's what your processor does. It doesn't wait for you to tell it execute this instruction. It says, I think you're going to go down that path. I'm going to execute these instructions. It doesn't throw out the data the moment you use it. It says, let me keep it around in my cache just in case you use it again. Or I think since you touched that, I'm going to fetch that other data, right? So we try to build this philosophy, this way of thinking about how to build machines into machine learning, right? And that's what a lot of other people are doing. I'm not saying this is something out of this universe, right? So the net effect of that is we would like to take that sea of multiply accumulate, eliminate as many as we can, and some of them make them less cost. But let's make this concrete. This is older work. This may be in some commercial chip already, who knows? It has to do with transferring data offset. One of the biggest overheads when you do run these networks, especially the newer ones, is the data transfers between your computing cores and your offset memory. And since we're in micro, I hope you're all familiar with these numbers, roughly speaking. When you go to offset, you typically spend 100 times the energy compared to getting your data from onset, and 50 to 100 times the latency. This is very slow and very expensive. So ideally, you would like to be able to do as much as possible on here and transfer as little as possible from this link. All right, so what do people do? People want to program. They don't want to optimize machines. So what they do is they say, let's pick a data type. In the beginning it was FP32, then it was int16, then it became int8. In some cases it's int4, in other cases it's int2, int3, whatever, right? So they pick a data type. Today for image classification networks, 8 is the standard, right? Everybody seems to believe that everything can be done with 8, and that's true, except in some cases like segmentation, stuff like that, where the actual applications are really not that interesting, but it's all these beautifying filters and stuff like that, where you have to get the edges very nice. I was told this information is a bit older, but they still have to do that in 16 bits to get good accuracy. Maybe they solved that. Anyway, what's the point here? They pick a data type for these things that's good enough to support the computation you need. What does it mean it's good enough? It's big enough to support any value that may ever appear. Right? Notice this is, remember the curve of effort versus reward? This is up on the corner. It says, what is the worst possible case I would ever need? Let me pick the data type so that it supports that. It makes perfect sense if you're programming. You don't want to be thinking about that. So at the machine level, when you transfer data from off-chip memory, you're going to get a packet of a bunch of values. That's how off-chip memory works. You don't access 1 byte or 4 bytes. You access 64 bytes or something like that. And then what you're going to do, inside that packet, you're going to put your numbers with the same container size. In this case, these are supposed to be, even though they're 7 bits, they're supposed to be 8. 8 bits regardless of what's the actual payload. Right? That's what it is. That's the simplest thing, very simple and everything. Now, this is regardless of what's the actual value in there. So the idea there is like the roll of range, right? One size of data to rule them all. Now, here's architecture, where architecture can help us. You analyze these networks, and you say, well, let's look at what we're actually transferring. If you look at image classification networks, and by the way, pretty much every other network, even for transformers, if you look at the data distribution, it looks like this. For image classification networks, it tends to be on the positive side. It's supposed to be 0. These are the positive numbers. And this is the distribution of values, which means how often this particular value appears. This is a mock diagram, and it shows that most of the data tends to be close to 0. Here, there's no person's line, very little data, if none. And then at the end, there are some that are spiking. These are important values. Because they say there's something there, maybe you should just look into it because it's related to you, or it's really the opposite of what you're looking for, right? So you have to support that. This is some actual data now. Good thing this room is kind of so small, so we can see it. This is Q8 bird, so it's a transformer, and this is a very older network by LSTM. What I want you to take from this figure is the following. This is a cumulative distribution. This is from 0 to 255. These are 8-bit networks. And this is the fraction of values, right? That's why at the end it goes to 1. Notice how it is, right? There is a bump. Half of your values are around very close to 0. Very little here. There is some, but very little. And then the rest are spiking. That's what's happening. And this applies to pretty much everything. Maybe we can try to reason why or not, but it's an empirical observation. Can I prove if my life depends on it? Will I put my hand over fire? Maybe not. But that's what we see every single time. So,
question,
yes.
On the right side, does that suggest that maybe even more than 8 bits should be being used by the application because everything's, it seems like stuff could be truncated?
To me, that's a very good point. I don't know. But to me, this says something else. It says that maybe 8 bit is too much. Because what we really need is we need, again, this is like an architect talking about machine learning, so take it with a huge grain of salt here. This is stuff that's somewhat interesting, maybe not really nothing here. And this is really interesting stuff. And we have a band of separation between to say, you know, this is how they're separated. By the way, we also found when people do quantization, right, because they tend to use 8 bits sometimes. If you look at how TensorFlow was doing quantization back in the day, and Python as well, you'll see that over here it's a bit more noisy sometimes. These are specific techniques for this network. The reason being is they just use the whole range even though they don't need it. They haven't tried to squeeze it down. We do have other work if you want to look it up, and other groups have done similar work. It's called bit pruning. The idea there is to train the network so that when you're training the same through backpropagation, in the same training algorithm, you learn what's the range you need. And what we find is the following, something that others have observed as well. The first and the last layer, they require a bit more, but not 8 bits. The layers in between is 2 to 4, something like that. This is if you use the same machine learning technique you learn to train, you augment the loss function to also ask it, can you please squeeze as much as you can? That's what you learn. So these things don't need 8 bits necessarily. Yes.
Is this how, like, would this be different for training? I mean, this diagram is this also for training?
This is what happens in training. What happens in training, again, sorry, keep qualifying, sorry, stop doing that, but keep that in mind. In the beginning, everything is random, right? So you have a uniform distribution. Very quickly, these things push like that, and then slowly they change. So it happens in training. You're going to see that because one of the techniques that what I told you, the floating point numbers, and you'll see that you need very short matrices, and the exponents are very narrow by default. We get to it often. Okay, good. Thanks for the interest. So what's our goal now as architects? We would like to plug in something here. This is our compute core, our own chip hierarchy. We would like to put something on the interface to external memory that will transparently use less bits to store the data here and expand it back to whatever works over there. This is a practical, why are we doing this? We're thinking, oh, company X has been working on 4 or 5 years to build this course, right? Okay, good. They know how to build that. They invested a lot of time and money to build this chip, right? What can we give them now to go to the next leapfrog generation if they can? So that's why we're putting this and transparently transfers the data using less bits. And that's the thinking behind it. So the idea here is fairly trivial at the end, completely unclimatic, but I like that stuff for architecture. I want something very simple, dumb as much as possible, little effort as possible. What we do is the following. Anytime we send data out of the chip, we ask, what's the highest magnitude value? This is the leading one position. You just look at all the bits, This is the most significant bit, this significant bit. You just look across the whole block you're transferring, you say, which is the highest value? Here, unfortunately, this requires the full container. We're going to store everything with the full container. But most of the time, you're going to get stuff like this. Right? Now, this is what changes the size of the container, which means that now we have to access data that takes less space. So they're going to be misaligned. But here's the thing, that's why the workload is very important. These are large tensors, large arrays, and guess how you're accessing them? Sequentially. Right? Even if you do blocking, you're going to take large portions of them and you're going to stream through them. So you couldn't care less how much space each block takes. You just need to know the beginning and the end. And the external memory just sees very nice sequential accesses, and external memory thanks you for that. Because DRAM likes that. Okay? At the end, with shapeshifter, whereas a conventional system will always transfer data using the same container, with shapeshifter you're going to see that. Now, time for some hard truths. This is a very busy graph because it has a lot of stuff. At some point in my life, I will fix it. Several networks. We can go talk specifics. This is normalized off-chip traffic. So 1 means what the baseline system will do. Some of them are 8-bit, some of them are less than 8-bit. And this is, we try to recreate IBM's PACT, which is 4 bits, right? The white is I want you to focus on the traffic. We'll see this graph later on for another technique. This is what the technique I just described does. It cuts down the traffic. Here, close to 40% is gone. Here, close to 20%. In other cases, close to 50%. So even though it's very trivial, very simple, it just works. Even for PACT that is F8-bit network, it saves a little bit. Just a tiny bit. Why? Because the distribution still applies. So far, so good. However, unfortunately, in some cases, like here, even in the PACT or this, you don't get much. So the next technique I'm going to describe is just going up that curve. We're going to put a little more effort, and we're going to get that. That technique is going to be the yellow stuff. Any questions up to this point? Yes, please.
So what kind of hardware would this need on the memory side? Like you need a comparator, a lot of comparators to do the comparison and find the range or something?
This is, okay, in terms of hardware, this sits on the memory controller side, it's on the chip. DRAM, you use standard DRAM, doesn't matter. This could actually be a compressor for your network traffic if you wish. It's on the chip. And finding, if you have a bunch of data, and you're trying to find what's the highest magnitude, once you deal with the sign, which is a fairly trivial operation to deal with the sign, you convert to sign magnitude. This is, you take the bit plane, and you ask all the bits in the bit plane. Again, you get an 8-bit mask here, and you do a leading one. So it's really trivial hardware. I don't know, I can show you the, we'll be happy to serve Verilog and everything with this stuff.
But we did say the energy in getting data from the DRAM if we are putting this in the DRAM controller, right?
Absolutely, because this thing is on your chip. This is tiny compared to everything else that happens on your chip. And compared to DRAM, remember it's 100x energy-wise, right? And 50x latency-wise. So this is an easy game to win on. You're saving a lot, that's the idea. And the other thing is, we have the equivalent technique for on your chip memory. I'm not going to present it today, right? The same thing we can do on the on-chip, in which case we amplify your capacity. Same number of bits, somehow you can hold more data. But you're right, that's exactly the trade-off. The way to see that this happens is to build a circuit, you synthesize, you can take down to layout. By the way, I don't know if you've done any time layout. We're talking about push-button layout. You get something like a spaghetti. This is not what you would actually build on your chip, but this is exactly what a company will do when they're investigating things. You get energy from that, you get models for your memory, you put the numbers down, and it does pan out. Energy-wise, this is golden. Very simple, and it saves quite a bit.
And sort of tack this from the another angle, software. Do I have to change my TensorFlow program or my PyTorch to know about this?
What somebody has to do is they have to change the low-level driver that does the DMA transfers, whatever it is. You tell it, start from here and to there. Just be aware of that. Right? So there is a software change, but it's not to the Python level or the TensorFlow or the PyTorch. It's not that thing. Basically, the level of data transfers from your memory. If you wish, you could keep the same container in memory occupied. There are a lot of you follow the memory compression work, but there is work on memory compression for general purpose systems where they keep the same area in memory, but they transfer less data. They pack the data more tightly, so they save all in bandwidth. We do that. All right, are you ready for the Big guns now? Okay, good. APAC. By the way, if you don't get anything out of this talk, if you haven't heard about arithmetic coding, it's an interesting thing, right? It's an interesting thing. It took me a while to grasp it. I'm at the level where I think I understand it. If you ask me, I did write the code because my student had some issues for personal things, so I had to, for the first time after several years, to write code myself. It was really fun at the end though. What is arithmetic coding? It's a compression technique, lossless, so you don't lose information, and it gives you nearly optimal encoding efficiency. I don't know if this is gonna be appreciated. When a value is very frequent, it will be encoded with less than a bit. This is very important. You will use less than a bit to store your zeros, for example, which happen to be very frequent in this net. Less than a bit. At the end, you will use an integer number of bits, but you have a million zeros, it will not be a million bits. It will be a lot less than a million bits. Right? That's the important thing with arithmetic coding. So what is arithmetic coding? Not my idea, of course. Bunch of numbers, pretend this is a tensor, a lot of numbers. What arithmetic coding does, it converts that into a real number. Just one real number. That's it. If I give you that real number, through the same algorithm, you can revert back and get that. The number of bits this has, it has to do with the entropy of this message. And by that I mean, what values appear and what is the relative frequency. You got to know this in advance, right? This works great for weights, and it works great for activations. Why? The activations you don't know statically, but when you run the network, the distribution of the values you get does not change much with the input for the activation. That's very important. You still get this bell curve, roughly speaking, this Gaussian distribution. The individual values do change, but if you were to look at the histogram, how often does that value appear? It doesn't change very much. So in advance, you have very good knowledge of what is the distribution of values here. Not which values are there or where they are, but what's the distribution. That's all that arithmetic coding needs. So the rest of this presentation for this part is going to be a short introduction to arithmetic coding, and then I'm going to tell you, we spend a lot of time trying to make this energy efficient, because if you go and you search the literature for arithmetic coding, I don't know, it's above my head. It's the goal there is to get as much efficiency as possible in coding efficiency, so the implementations have to be very heavy duty, very, they require very expensive hardware. Remember, we're trying to do this: compute cores, on-chip memory, compressor here, and we want to transparently use less bits here, and expand back to whatever they're using internally. I'm going to show you for fixed point. This works wonders for exponents for floating point too. All right. Remember the distribution, right? That's the distribution. Let's take
exponents for floating point, not mantissa.
Mantissa, we have another technique for that. I'll explain what's going on with mantissas. It has to do with the normalization. It's the next, it's the last thing, hopefully, by 1 p.m. I'm going to get to it. All right. I'm trying to be funny, but we'll see. Okay, good. So let's say we have a distribution, right? 4 values, so we can track because we're humans. I'm not going to do 56. So we have 4 values, A, B, C, and D. It doesn't matter. That's the whole point. It's symbols in arithmetic coding terminology. It can be anything you want, right? There are 4 things. And we're going to try to encode them into a real number. What we know in advance is the relative frequency of this. By the way, if you don't know the frequency very well, you're going to get less efficiency of your encoding. Still going to be very good, as long as you're ballpark okay. Here's the key with arithmetic coding. You start with a range, and as you get more and more symbols, you squeeze your range. You start with a range of 0 to 1. Think of this like probabilities, right? And as we're going to be getting more and more symbols, we're going to be narrowing this down. But here's the trick. How we're going to be narrowing it, it has to do with the symbols we've seen so far. So the first thing with arithmetic coding is to create a table that says, take the range of 0 to 1, split it into sub-ranges that have to do with the frequency of the symbols. Notice that the sub-ranges are exactly the frequencies. But the next important thing is, make them non-overlapping. So for every symbol, you have a range and an offset that's in stars, right? So you have a specific beginning and end. So how do we encode? In the beginning of time, there was nothing, right? And then you said, right now, I haven't seen anything. So my range is the full 0 to 1. Then I say, well, A. What do I do? Well, I squeeze down, this is easy in this case, right? I squeeze down my range to 0 and 0.4. Why? Because A corresponds to this subrange. specifically. I moved only the high below there, right? And the low stayed there because that's exactly the subrange that corresponds to A. Does that make sense? As the encoding process proceeds, what's going to be happening is high and low are going to get in closer and closer. But they will never touch, because you have to think about this in the pure mathematical sense. Right? These will keep getting digits, and it will become closer and closer and closer. The number of digits you're going to need depends on what you've seen so far. So that's the difficulty in implementing this in hardware. Right? You will need infinite precision. Actually, you need precision that's proportional to the frequency of the symbols and how many you've seen so far. You may end up, in our case, you're going to be needing numbers that have, I don't know, 64K bits or more than that. It doesn't matter. We're going to see how you can build effective hardware with that. All right. So now we've seen the A. We take this table conceptually and we map it down to our new subrange. So what we've done now is we take this and we say if our new subrange is this and the frequency of the symbols is what we want, this is the new table. So if the next thing you see in A is an A, you should stay here. If the next thing you see is a B, you should go here. If the next thing you see is a C, you should go here. Notice that as we move, digits start appearing, even in the decimal system. Right? So now if we see a B, the calculation is there. You can get the slides, I guess. Once we see a B, we have to take the corresponding 0.1 position, so we're going to pick a number between here and here. So our high is going to become this, our low is going to become that, so on and so forth. All right? Now, by the way, there are levels of understanding. The first level of understanding is somebody tells you something or you read something and you thought you understood what you read. And then you try to write it on your own, it becomes hard because you haven't really grasped. So it took me a while to get to that second stage. Even getting here was hard for me. Right? So I'll leave this with Eric and you can look at them when you want. There's more examples there. Let's talk architecture now. What's the problem with this? First of all, if you look at the algorithm, it requires multiplication, division with arbitrary precision numbers, real numbers. That's not very nice. It's very expensive. Second thing, it requires these probability tables I showed you, those ranges. And if you have, say, even an 8-bit network, this thing has to have 256 registers inside, table. It's going to be expensive because you have to search where you are and how you fall, all this kind of stuff. And last part, the algorithm, the classical algorithm, gives you a bit at a time. One bit. So horrible, 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 because guess what? For machine learning, you need high bandwidth. So what we've done, and this is the key idea behind A part, and again, well, I'm sorry this is not super exciting or anything like that, it's something very simple now, but I like that, is we're going to express the numbers into two portions. The first is going to be a prefix of the number, and the next is going to be an offset. So for example, 0, if it's very frequent, is going to be represented with a full range of its own, no offset whatsoever, it's just a value 0. And so that at the end, it ends up being recorded with less than a digit. This number, for example, is somewhere in the no man's land, in between. We're going to be using a very short prefix, which means a very large range and a very large offset. Why? Okay, because this is very infrequent. I don't care to have much efficiency, and this is going to happen once in the blue moon. So what we do is we profile the network. We take the weights and we create a histogram of their frequencies, the values, per layer. We take the activations, we run a bunch of examples, we get a distribution for those. For those two distributions, separately for the weights for the activations, you get something like this, a histogram, and then you run a simple algorithm. It's really first cut version. It's a stupid algorithm, but it works. It's an exhaustive search that stops after a while. And what it does, it says the following. If I'm going to be encoding numbers as base, prefix plus offset, and I'm going to encode, that's the second part in green of the solution, only this is going to be encoded using arithmetic coding. This is going to be stored as is, just the bits, right? Find me a separation, find me subranges that give me good encoding efficiency. Values that are very frequent, they're going to be assigned to very short ranges, so they have very few offset bits. And I'm going to be taking advantage of the arithmetic coding power. Numbers that are in between here that don't have much frequency, I'm going to give them a huge range, very short prefix, and then very large offset. At the end, I want to minimize how much space I take in main memory. And we're going to build hardware that actually does one value at a time, and we're going to use 32 of those in parallel. Why can we do that? Because remember, lots of data, sequential accesses, we can do that. It's not a problem for this worker. You cannot do this for general purpose systems because you don't have this kind of big arrays that you access sequentially. So I don't know if you mentioned it.
question in terms of general purpose systems. This seems in some ways similar to Huffman encoding, which is used in lots of just software compression techniques.
Absolutely.
And what you're compressing in some level is a giant array. So, and could your acceleration help just software compress gzip, gzip, that sort of thing?
I don't know. Software, arithmetic coding has been tons of work. A lot of the video encoders actually use arithmetic coding as well inside. Anytime you have lots of data, people will use it. Software can afford to be slow. Right? For hardware, it's a tricky thing. Huffman coding is you can do that, even though I'm pretty sure Huffman will not appreciate that. Is a special case of this where the distribution here is everything is about to. Now, I impress you with my deep knowledge, but I spent a lot of months learning this stuff. That's why I know this comes so easy. It wasn't easy for me to get it. But that's what Huffman coding is. Huffman is matches arithmetic coding. Only when you histogram, the bars are powers of 2. Then it's the same thing. Otherwise, it's Huffman coding will always use an integer number of bits. That's the whole point. Fair enough? All right. Now, this is an actual table here. This is not everything that's stored. Actually, in hardware, we only store some of these things. What you see here is the following. This is from a layer of BioSPM. And I want to make some points so that you're going to appreciate them. This says the value range. Notice it says from 0 to 3. So there are 4 values. So the offset is going to be 2 bits. So every number in that range is going to be encoded as the symbol 0. How many bits that means? Maybe we need a fractional number of bits. And then 2 extra offset bits. So I'm going to have 2 strings, both sequential. Now, these are our probabilities. Remember the range? We use 10 bits. Right? This is another compromise we're making. We're not going to be using any arbitrary probability here because that's what your distribution will require. We're going to cut it down to 10 bits. So think of this as a fixed point number with what the dot is before. So 3FF is the 1, 0.999999, right? Now, notice this. This range is 2 numbers. This range is 4 numbers, 4 numbers. This is 8 numbers. This is a lot more, 64. The algorithm figured this out. This is a good allocation of ranges according to the distribution of this layer. This table is tiny. It's only 16 entries, and in many layers you can do 8 if you want, and you're still going to be okay. The other thing is look at the probabilities. This is the actual number they represent. Look at these guys. Zeros. Why? Because this is weights. Those values never appear. This has been quantized, and those things don't appear. And notice how high the distribution of zeros is in this particular layer. Right? It's close to 50. Sorry, the values between 0 and 3. Sorry, not zeros. Now, how can we build hardware for that? Well, again, I say you can find papers that say, efficient hardware implementation, whatever. I don't know. They all fly through my head. There's a lot of math over there. Sorry, I left it in high school. But here's a realization. Remember the high and low, the 2 numbers? As this thing progresses, these things get closer and closer. If you look at the binary representation of that, this means what? That as they're getting closer and closer, there's going to be a prefix of things that never changes from that point on. Because they get closer and closer. All the action is going to be back here. So you could build fixed point hardware as long as you are very careful how you do that. We found an algorithm written in C 20 years ago that was doing that, but the algorithm is incremental. It does a bit at a time. So our engineering effort now, I find nothing wrong with engineering because at the end, all of this stuff has to be materialized in actual hardware, was we came up with this thing. And I'm not going to go through that. There's no way I can explain that. I'll be happy to give you the sequence so you can follow how it does things. This produces a value per cycle, and you have several of those open in parallel. What I want to point out is the following. This produces a value per cycle. Only the gray stuff are registers. There's 16 of them. This is the base and how many offset bits. And these are the probabilities. And we only need to keep one of them because the other one is the next guy. And these are the 2 high-low registers. This is an interesting thing. You cannot guarantee always that you can do the calculations with how many bits you pick for precision. So sometimes when you see that the high and the low are getting very close, you have to do some tricks to make sure that they never cross each other. You never lose track. Everything else you see is combinatorial logic. And this thing, the whole thing can run in 500 megahertz and 65 nanometers if you want, without pipelining, without anything. If you want to pipeline it, there's tons of opportunities. All right. our favorite graph now. Same graph as before. Some networks we managed to collect, and black is the baseline, safe sitter is the white thing, the easy technique. Yellow is the APAC. And lo and behold, even for a 4-bit network, it does find stuff to do. Why? Because 4 bits, 4 bits. If you save a bit, it's 25%, right? And the distribution is the same. It's squeezed, but it's the same one. So it gives you that. For many others, it doesn't. Overall, it does much better than safe sitter because it doesn't. First of all, it doesn't use the integer number of bits, and it doesn't care whether you're in a group or not. It looks at your frequency, the individual. Next thing, ignore this thing. This is stuff that reviewers want to see every time. I don't know why. And this is the arithmetic coding. This is what the original arithmetic coding will do. Right? So in most cases, we got very close. We have to compare this with the yellow. We lose some efficiency in some cases, but now the segment we're down to close to 25%, at 1/4 of the traffic, and we lose 2-3% from that. So I think this is a good trade-off. Yes, please.
So the precision of this model is all 8 bits, the baseline bits.
All of these are 8 bits, yeah, except for some of them, this is 4. And this is an Intel thing, the Q, that one of the sites, I think the weights are logarithmic. The nice thing about both techniques I told you is that if tomorrow you manage to quantize to 6 bits, it will give you something. If you quantize to 5 bits, it will follow you. Right? It doesn't require you. Just need to tell you this is the highest you need. Yes, please.
So you mentioned that some networks like segmentation and stuff like that will require like 16 bits. Would you expect to see bigger gains there? Since
Absolutely. Because there's a lot more opportunity to say. The distribution is very similar, and there's a lot more opportunity. All right. Yes, sir.
So, in this experience, is it only on the weights or also the activation?
Both.
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 So,
And this is sorry, this is calculation.
oh, sorry. So how about in terms of the performance? Because for generating the activations, like let's say tau by tau, and you have to like analyze their distributions and one by one, generating one value by one value. Isn't it kind of increase the latency?
Yeah, no, I understand where this question is coming from. Sorry, I didn't explain it well. Before you run a network, you profile it. And for every layer, you create 2 tables of 16 entry 6. The 2 tables effectively represent the distributions you've seen when you profile.
Okay, so it's like an offline collaboration to refine the.
Yeah, and this algorithm, the one I was trying to show before, this one, sorry, this guy here, he captures that. And let me make that comment again. Hopefully this time is the right time to make it. For activations, you don't know what the individual values will be, but once you collect this, it looks very similar across all inputs. It changes a little bit, but the distribution is very close. So it's noise. I mean, it literally is in the 3rd decimal digit, the differences in compression you're going to get if you do specific, because the distribution remains the same. So all of this is done offline. At runtime, as you're outputting activations, you compress them. Right? And since you have tons of units, you can do that at the output of each one. And it's 1 value per cycle. And remember, to produce 1 value for this network, if it's anything, right, convolution layers or a fully connected layer, you do a lot of computations. You don't do 1 cycle to produce a value. I don't know if that makes sense. For every output neuron, you spend a lot of cycles to produce it. So you have plenty of time to compress it as well on the output for activations. For weights, you do it offline. It's already prepackaged. All right.
Actually,
What
one more
day is this?
question for you. So there are a lot of applications that are still using 64 bits, fluid dynamics, partial differential equations, solvers, and all that sort of thing. It seems like, I don't know what the distributions are there, but it seems like there could be a lot of opportunity apropos of the 16-bit question.
Yeah, there might be. I don't know. I'm not quite sure those applications, the distributions are very favorable. I don't know. But these are very skewed distributions. All right. So these slides were not made by me. You can tell that. So somebody that does really enjoy making slides, and they had some time. So this is more key, which is how can we take transformers, very family, and run a fixed point inference with them, and actually squeeze them down to something much smaller. And I guess
I mean, unfortunately, since Yuan Low is the scheduled next speaker is ill, you can't take as much time as you want.
Yeah, I'm okay, whatever you want. I mean, already some people left, so I'm finding a way, I'm not gonna be offended. I can go very fast, or we can take a break and see whatever you want.
Everybody wants to stop, fine. I'm interested, I would like to hear more.
All right, thank you for being so kind to me. All right. Everybody likes attention, right? Good. So, you know the problem with the bird models. They keep growing and growing and growing the transformers, right? And now they're even beyond this, the 2 terabyte. And the other part is that if you do small sentences as inputs, the activations are a small fraction, so the game is the weight. But once you start looking at more stuff, unless some other technique comes up, this becomes very important activation. And the problem with activations is they're runtime calculated values. So in memory is the bottleneck for this thing, regardless, right? So, and the final thing is that they do floating point compute for the most part. There are some attempts to make them integers. They have some success, still you're losing something. So what is Markey? Markey is a technique that will take a bird-like model, and when you specialize it, post-training, you don't need to retrain it, it will convert it to something that will require 4-bit indexes. So we'll convert the values, we try this for FP32 and FP16. The compression rate is this, obviously, right? It's effectively a dictionary-based quantization, if you're not familiar with deep compression from Soundhound and Bill Daly, along the same vein. But the other important thing here is, besides that it's for transformers, is that we never need to convert back to the original values. Never. This quantization has a funky property so that at the end, we're going to be saying on the first value, on the second value, on the third value, and we're going to compute based on that. We're not going to say, well, the first value or the value 10. No, we're just going to compute with the fact that I'm over the first, the second, or the third, or the fourth value. So Markey does, when you quantize, you're not quantizing to arbitrary centroids. That's what dictionary is. You say on the first value, and there's this value, but there's going to be a close formula of what these values are. It doesn't require retraining. It's force training. When you take a network and you specialize into a particular task, that's all what you need. And then we are not going to be doing multiply accumulate. We're going to be counting indexes for the most part. The gap is going to be one multiplication, and these are going to be done with 16-bit. Even those computations at the end is going to be with fixed point. Everything. So marketing slide, this is how much it saves you compared to some model of tensor cores, 15 times faster, 100 times faster. We don't have a lot of other techniques that do this kind of thing. This is because we're very early into the transformer game. And right now they're floating point. And this is if you decide to go all the way in. Do both memory compression for bit indexes and compute units. If you decide to just do memory compression, you can get this. And it does make a big difference in terms of energy efficiency because memory is expensive. That's why. All right, so some lessons learned from this. I'm going to go through this quickly. First thing, this is Ali that did this work. This is purely his work. I was just learning through it. He found the following. These are the distributions for transformer layers. These are weights, but similar things apply for activation. Look at the shape. Right? As humans, we can see the same shape. Right? It's slightly different, the scale, but it's the same shape. So pretty much, all the layers follow a very similar distribution. What changes is what is the zero and how spread out it is. So what he does is he creates one reference distribution. He quantizes this, and then he expresses every other layer by just 2 parameters, the mean and the standard deviation. That's the first thing. Very quick quantization. You don't need to quantize every layer. You want to have million layers 10 years down the line? Fine. Just create one standard distribution, and then everything else becomes that. That's the first thing, practical thing. The next thing is the following. This is the original network. You have an activation and weight. They're both floating point numbers. You have to do multiply accumulate with floating point. If you do dictionary quantization, like deep compression, nothing wrong with it. I'm just saying this is the way it is, right? You convert the values into indexes. You have a dictionary, right? And then you say the first value is the 0.2, the third value is the 1.1. When you need to do compute, you take these two values out of this table. There's a lookup everywhere. Anytime you need the values to do the computation, you need to look it up. Either when you bring it from memory or next to the multiplier, somewhere you need a table to do the lookup. You get these two, you get the value. And Moki, what it does, it says the following. What I told you before. I'm the first value, I'm the second value. Well, I will do this calculation like this. How I'm going to get that? And this is the part that, sorry for being too enthusiastic about, blew my mind. That's his idea, right? He did the following. The values that he ends up using as centroids, these are the representing values, they're all of a closed formula of two parameters. These are fixed values, and this is the index. But these ones are chosen according to the layer. So he takes statistics, and he chooses this. And then there's a whole page of math that says once you do that, guess what? Multiply accumulates a lot of them, ends up being a histogram of how many times each one of them appears, plus some scaling factors at the end.
Just nomenclature, that I is not imaginary.
No, sorry, yeah, somebody else has asked that. So you're not the first one, so that's a fair question, I guess, at this point. All right, good. So how does he achieve that? He gets that distribution I told you before. Remember the one I was showing you before? Sorry. We have this wonderful thing. There's a distribution here, and you get this shape. Look at that side. Right? He takes that shape and says, okay, let's do a curve fitting now. And it's approximation of the approximation of approximation. So these are the original values, the black ones, right? The dots. And then he does an exponential fittings. He says, give me an exponential that if I restrict it to this range, the shape looks very close to that. This is really ad hoc, isn't it? I mean, to me, it's okay, fine, whatever. I mean, since we're doing quantization, what the heck, let's do this too. And he ends up with this. And then everything works like magic. And I'm going to step out now and pretend that everything is understood. Anyway, you can read the papers in this case this here, explains that. And at the end, blah, 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 because we don't have much time. I guess I want to get to the last point and then stop. Accuracy very close, we do lose a bit, and that's it. He does work with fairly sizable networks for an academic group, and energy efficiency is through the roof. Because remember, I mean, it's like the other machine is using FP16 and FP32, but of course. That's as much as I want to say for Monkey.
The graph you showed, the distribution is so similar across all these things except for the height and so forth. And that seems like it could be an artifact of the central limit theorem. And so to sort of follow the theme I've asked before, could this be potentially more broadly useful? Because obviously if you have large numbers in anything, you're likely to get that sort of distribution.
You know, Eric, sorry, look, there's the right answers to give you, and the one I really want to give you is the following. I really regret in undergrad, I didn't pay much attention to statistics. You're probably right. I honestly regret not paying. I really regret, so, take it from me, that I know what I'm talking about. If you still have the chance to read about statistics and probability, computer science has changed forever, right? We're no longer the place where we work with numbers and we can reason about them. It's just tons of data. So that stuff is really important. Sorry for being not capable of rising to the occasion.
Yes, I was worried about being asked about
very
all the
important.
many things I don't know.
All right. By the way, every time you submit this, people say, this has nothing to do with quantum physics. Yes, it doesn't. This is just marketing. And you're right, absolutely. Nothing to do with it. So here's the thing. This is Milos's came up with this idea. We have the training process. And you have a network, and every layer you go forward pass, and then you go backward pass. The unfortunate part is the following. In the forward pass, you create these activations, and you need them in the backward pass to calculate the gradients, so you can do the updates. The unfortunate part is the naive version of training requires that you stash all of those, save them somewhere, then recover them. And that somewhere is memory. Now, there's tons of work on how to optimize that. That you can recompute, you can partition, whatever, but at the end, there's a lot of them, and you have to recover them. Maybe not all of them, or not. So, training right now is mostly done with FP32. There's default 16, there's FP16, and I think 2 or 3 weeks ago, a group of people from NVIDIA want FP8, or maybe they already have FP8. And they have different formats underneath. So the problem we have been working for 2 years now is, can we come up with a piece of hardware or software that is hidden from you as much as possible, that will take this and say, okay, start with this because you know this is going to converge, and then do your magic and somehow squeeze this. Right? Squeeze this. And what is the challenge? Exponents. We knew this for quite some time. There's not much range here. The exponent distribution, it's a fixed point number really, it's a biased fixed point number, and most exponents are very small, they're very close to zero. So take APAC, take shapeshifter, it kills it. Right? You cut this down to nothing. Right? So that's easy. You don't learn it, but you can squeeze it. Right? We're working on trying to learn it. Mantisas, however, because they're normalized, if you look at the distribution, you don't have a Gaussian distribution anymore. The values might be Gaussian, but the mantissa representation is not. It's a uniform, pretty much. Why? If the number is large, there's a lot of noise. If the number is small, there's a lot of noise, right? But you just don't know how much noise is there. You just don't. So what can we do? So what the techniques, I'm going to present two techniques briefly. One is a machine learning approach. It changes the learning algorithm. Sorry, it doesn't change the algorithm. It takes advantage of the exact same algorithm to also learn this. And the other one is like a computer architecture approach. It's training as a black box and just throws things at it and see what it does. Now, so here's what the first technique, fittingly is called quantum mantissa. So what am I showing you here? It shows you the length of the mantissa, starting from something that is a 16-bit floating point number, and how quantum mantissa adapts that over time. These are epochs. This is the result 18, we're an academic group. And what you see here is the average bit length of the mantissa. I don't know if you can see the color. The one below is the activations. The one above is the weights. Okay? So when we look at the average, look at it. And at the end, when we actually go to, we bump it up a little bit so that we get an integer number of it, because we're learning this. We get fractional mantissa. We simulate those. Sorry, I'm confusing you. Anyway, at the end, we'll be around 2 on average. What are the bands? I mean, maybe you already have guessed it, but if not, the bands are, if you look at all the layers, what's the actual range? What's the minimum you see? What is the maximum you see? And this includes, I think, the normalized one. So there are some layers that we don't need any. They're really logarithmic. That's what it is. But the algorithm learns this, and it learns it very, very quickly. See that? That's the thing. Even if you stop, actually we looked at the log the other day, last week, and after a few batches, you get very close to this number. Certainly at the end of the first epoch. Certainly at the end of the second epoch, you already converge to your minimum, pretty much. And this is the accuracy. The baseline is the red, the blue is the quantum mantissa. So notice that they're tagging along. At the end, we're losing just below 0.5 in absolute. And this is without any tuning or anything like that. We haven't played with the parameters. We're trying to squeeze as much as possible. I suspect that if we say squeeze less, this is going to match it, no problem. How is this done? I don't know if this was on the slide before. We take the loss function and we introduce at the end, somewhere there, sorry, this is I don't have the formula. We take the loss function, we add an extra parameter there that says, try to minimize the mantissa bit. That's all there is. It's as simple as that. And then there is some tricks on how you can do this with less computation, and how do you take something that is not differentiable, bit length, because it's an integer, and you convert it into a smooth function. It's all in the paper, even I understand that. So far so good? Last thing, then we're done. You're a very good crowd, thank you. Bit swap. Now, I'm an architect at heart, right? So you tell me you want to adjust something, I remember the following. Machines are very fast things. They do billions of computations per second. So a classical technique now in architecture is when you have a parameter you need to adjust, well, you try things for a short amount of time, you see what works, and then you use it. So what's the idea behind Big Sur? Forget about changing the training algorithm, adding loss functions and stuff like that. Just look at the output. You see, I'm looking at the loss. This is an indication of progress. Is the loss improving? If it is improving, come on, we cut and anticipate for some time. Then we ask again, is the loss still improving? Well, cut more. Oops, the loss is not improving. Give it anticipate time, right? The training itself is, unless you push it too hard, it's a self-healing process. And you do a lot of it. There's a lot of trials, right? You do batches, there's many batches per epoch, and you do a lot of epochs. So there's a lot of opportunities to be wrong and still make up for it. Right? Now, the other important thing with this is that the loss is not a monotonic function. Right? The loss is going up and down. So you have to have some tolerance there to say, okay, I think we're doing okay. So we use an exponential average. We say, what was the last batch? Put into a formula and smooth it out. And we're looking at the trend. As long as the trend is improving, we cut mantis a bit. If the trend starts degrading, we increase the mantis a bit. Stupid enough? Simple enough? Well, it works. It doesn't work as well as the other one, because this is not network-wide. Sorry, this is not per layer. This is network-wide. But, so this is with 32 bits now, but it does cut down the mantissa bits, but it's much, much noisier. This is the mantissa length that it gets. This is a pure, if you wish, hardware or firmware approach. It doesn't care about what you do. It just needs to be told, this is the loss, this is the loss, this is the loss. Just think, writing a single register per epoch. And this is the accuracy we get. Surprisingly, it gets identical with quantum mantissa pretty much, but it's a much noisier process. Because it treats it as a black box, that's it. All right, so you've been a wonderful crowd. I appreciate that. I'm going to stop here. There's the data that shows how well it does. It's going to be there. And I'll stop here. And thank you for your time. It's wonderful to be back in Chicago even for half a day. It's nice to be in the crowd. It's very nice of you. Thank you. And I'm happy to discuss anything you want, or we can have coffee. Yes.
So for the work you're doing about reduced precision, are you considering arbitrary bit lengths, or are you restricting this just to lengths where you still have line memory accesses?
You don't have to restrict to that because you naturally get those. The way the hardware is built, there is an engine that talks to the memory controller, and you inform that engine how to get attention. So what you give that engine, you give a beginning and a length. And it starts fetching data as it needs. The request to offset memory, they're always aligned. Internally, that thing, the way the things are packed, it just unpacks them into whatever data type then the unit requires inside. And I understand, I don't want to guess what you're thinking, but there is an issue always with misalignment and how much the data is packed in a nice way so that you don't have huge crossbars. Our crossbars tend to be a crossbar that has as many bits as the biggest data type you want to support. So if your network ever is going to use 16 bits, we have 16 by 16 crossbars, not what's your memory width in kilobits or what's your internal memory width, not that. That's the thing with these workers. Large accesses, sequential. That's what you're asking about.
So you mentioned that these techniques you get potentially an order of 100x energy savings.
From what?
Right. So how close does that get you to biological systems? Right, the brain uses like 20 watts, and we've got orders and orders of magnitude off the brain, obviously.
Yeah.
So do you have a sense of how, if I get your 100x, how close am I to biology?
This is compared to something that is really horrible, right? That was the thing. I don't know how close we are, but I don't think we're even. I think we're several orders of magnitude away. Even if we assume what these things are thinking, it's good enough. We do have another project. There's a person in Toronto. He's a brain surgeon, let's say it like that. And they're doing, I think I recently found out that there's other work not familiar with that, but came before this, I didn't know, Halo, and new brain this guy. They do implant things into brains of people that have serious issues, and they do use them in animals for studies and stuff like that. There's a lot of work to be done over there, and machine learning has a key role to play, because it's a lot of pattern matching in those. goes that if you can capture signals from the brain and you can correlate the signals you're capturing with neuron groups, and then you look at the periods of time, you can potentially start grasping what that entity is thinking. And there is some work from other people, not nothing to do with it, where people can speak even though they cannot speak. There are challenges with this technology. The probes are moving, but it's very interesting stuff because at the end you have tiny little radars inside your brain. And it's all part of muscle. And their energy efficiency becomes huge. We want this next to course. All right.
Sorry, Mark. I don't know if you'll be able to stay early this afternoon, but we've got a talk at 1 o'clock, I believe, from Sabaticos from the UIUC. And he's going to be talking, I think, a lot about edge devices where obviously energy is very important. So I don't have a real question, but it'd just be interesting if you're here to sort of see if all these those techniques you described might be, how applicable they would be.
No, there's a lot of interesting work at the edge. I think it's a very exciting field. There is definitely a lot of interest from industry as well. And there's a lot of opportunity to have a real impact in life as well. I'm not sure how it's going to be the one that will do it, because the likes of IBM, NVIDIA, Intel, whatever, they have a good grasp of stuff. That's why we're working on this like this, right? But it's a very interesting field, and sorry for being a bit self-centered. I'm having some fun with it. It's an interesting field to work on. Compared to the general purpose stuff, you say, look, mom, I got 0.5%. By the way, mostly the 100Xs and stuff like that is because the baseline machines are so inefficient, they still use floating point, right? And we go from floating point calculations down to 4-bit counting. We had a talk at some point with some VC, and I was telling them, oh, you know what, with this technique, we can give you 2X. And he told me, by the way, unless you can give me 10X, I'm not interested. My response to them, of course, was, if anybody tells you they can give you 10X, I don't know. I have a, the classical thing is to say, I have a place to send you, right? But still, that's the expectation. You're not going to get 100X for that stuff. I have to live by one, so I'm going to stay up to one if I need to. Okay, so we can have an open discussion, we can grab coffee, whatever you guys want. When is the next talk? Maybe you guys can tell us what you guys are working on.
So the next talk will be at 11 o'clock.
Oh,
Actually, unfortunately, this is another case where the speaker actually cannot physically be present, so we have a